Thank you. I would have really forgotten today. Okay, so I have some issue with my index finger. I'm hoping I'll be able to write. If I can't write, then yeah, you'll have to take this hour off or something. All right, seems okay. Seems not to hurt too much. Okay, so that is because I have something written on the top, and that is with your yesterday's notes which I uploaded. So let's start off. What were we talking about yesterday? We were talking about the simple harmonic oscillator, right? And we were talking about a one dimensional simple harmonic oscillator. This is not a 3D oscillator, it's a one dimensional simple harmonic oscillator. Just 1 second, I need to admit two more people. Okay. And what we talked about yesterday is, firstly, we tried to write down the Hamiltonian. And the Hamiltonian, we know, is always the kinetic energy, which we will write it like this. Okay. Uh, any issues? Any doubts, please? Or somebody unmuted by mistake? Any doubts, please? Okay, I'll please speak up. Okay, if you have any doubts, I'll clear it. Not an issue. Plus, you have the potential energy, and some people very correctly told me yesterday, and I was really very happy with your batch. That is for a harmonic oscillator. It is half kx square. But then we use this relation omega is equal to k by m to write down the k as equal to m omega square. So essentially we now have this px square by 2m plus we have half m omega square x square. Then what do we do? This, of course, you can ask, how did we know this before? So yes, there is a bit of artificiality about the next step, but what you have to realize is, once people realize the solution was a particular way, they went back and they modified their earlier steps so that the next few steps would become simpler and more elegant. Okay, so what is it that you do? You take out an h cross omega by 2 common, and what you end up with is 1 upon m h cross omega, which you realize is a number, into px square plus m omega by h cross into x square, right? And as I told you yesterday, this is as if you have a operator. Okay, your Hamiltonian is like an operator which is equal to some operator c square plus another operator d square. Okay, and then how do you normally write a c square plus a d square? You would write it as c plus id into c minus id. But if this is only if C and D are numbers, okay, and if they are numbers, we know that CD is equal to DC, right? That means they commute. However, okay, in this particular case, you realize there is a px square and there is an x square, okay, and thereby we are talking about commutation at least of x and p, x, and we know that x and px, position and momentum, do not commute. Okay, so in the case where, okay, CD is not equal to DC, okay, then what do? You have to write this c square plus d square as equal to, what is it, half of c plus id into C minus ID plus half of, I've just put half with each one of them, C minus ID into C plus ID, right? And thereby you would have C plus ID by root 2, this operator, into C minus ID by root 2 plus half, plus C minus ID by root 2 into C plus ID by root 2. Okay. So now what do? We essentially define our A plus and our A minus. How do we do that? As I told you yesterday, we thereby define, as I said, our we define these new operators. One which we call as an A plus. Let me just check it out so that I don't get it wrong. Okay, which we essentially write it down as 1 upon root 2. Okay, your m omega by h cross power half x minus I, 1 upon m h cross omega power half px, and the other one you call as A minus. Remember, this is a definition. Okay, this is a definition. Okay, somebody else is waiting. I'll just admit the person, and that is 1 by root 2. Okay, and here you have what? M omega by h cross power half x plus I, 1 upon m omega m h cross omega power half px. Okay, you define these two, and then what do you get? You essentially get, let me just change the page. Okay, over here as well, you will get your Hamiltonian equal to, what is it? H cross omega by 2 into A minus A plus A plus A minus. Okay, so this is the what we have done. We have cast the Hamiltonian in terms of two new operators, A minus A plus, instead of what was there earlier, x square and px square. Is this clear to everybody? What we have done? Is the mathematics clear? Has everybody understood this? What happened? I know it's the last hour of the day. Please make an effort. Have you understood this? If you have doubts, I will explain again.
Yes.
It's okay? Amruta, is this okay? Have you understood?
Yes, ma'am.
Okay, good. Okay, so somebody else. All right, so let's proceed from here. Okay, now that you have two new operators, okay, the first thing we have to ask ourselves is what are the properties of these operators? And secondly, if you realize there's something very peculiar here. Okay, I have called, see, look at it over here. There is a minus sign here, and yet I am calling it an A plus, and there is a plus sign here, and yet I'm calling it A minus. Okay, and why is that? You will realize later on. I was telling you yesterday that these operators you find actually have the ability to change the energy levels of the system. Okay, so now remember, what do you do in quantum mechanics? You try to find the wave function. How do you try to find the wave function? By solving the Schrodinger equation. Okay, and as you realize, the Schrodinger equation, what does it do? Usually if it is a time independent potential, okay, which I hopefully Meera ma'am would have already talked to you about that. If it is a time independent potential, then you can write down the time independent Schrodinger equation, right? And that, if you realize, is nothing but an eigenvalue equation. It's an eigenvalue equation which says some h, which is your Hamiltonian psi, is equal to, what is it? Is equal to E psi, right? And what you do is that after writing it down, you try to solve for this psi. Okay. Now, the point is what you are, okay, why did I come to this now? I have now forgotten why I started this argument. Okay, it doesn't matter. Okay, so this is what you try to do in the Schrodinger equation. Now, the point is that what you're trying to do is you're trying to solve for the psi. Not only the psi, you're also trying to solve for which values of E you can actually use. So you are solving for energy eigen values, which are what? The E. Okay, you're also solving for the energy eigenstate. Okay, which are the size. Okay, so there may not be just one. So in general we write it like this. Okay, En psi. Okay, in general you will write it like this. Now what I'm trying to tell you is that the A plus, A minus and A plus actually help you change the psi n. Okay, so if you do an A plus upon the psi n, you will actually end up with something, some constant term psi n plus 1. Okay, similarly if you did A minus psi n, you will end up with some constant psi n minus 1. So these two are called the ladder operators. Okay, why is that? They are helping you climb up or climb down the energy level operator. Okay, also what you have to remember, I'll have to quickly move off to the next page before I start scribbling on things. Okay, also what you have to realize is that okay, I think yeah, so this A minus, since it brings you down, okay, it goes from n to n minus 1, it is called lowering operator. Okay, it's called the lowering operator because it lowers your step. And what is this one called? It is called the raising operator. Okay, of course I haven't yet proved all this to you. I'm going to start doing it now, but this is the logic behind it, and you will find how bringing in these two operators, finding out their properties, okay, actually helps us solve the uh, the problem of the one dimensional oscillator in a very neat and elegant way. Okay, so I will now move on to the next page. Okay, and I've written a whole bunch of stuff. Okay, doesn't matter. Now, so first thing we will do is we will try and understand these operator. The very first thing that you have to realize, okay, is that uh, yeah, you know that x and px are both Hermitian. Okay, how do we know they are both Hermitian? Sorry, I put an extra e there. We know they are both Hermitian simply because they are associated with real physical variables. Okay, I mean, you don't need to really get into that, but you can prove it also. But right now what you need to keep in your heads is that they are associated with real dynamical variables, then they have to be associated with operators that are Hermitian. Okay, so you can take the logic one way or the other. All right, now, the other thing that you have to remember is that this x and px do not commute. Okay, they do not commute, and their commutation is like this: x px is equal to ih cross, and this I'm hoping that you have done already with Meera ma'am. So now, ask the first question is: are a plus and a minus Hermitian? Okay, are they Hermitian is the question that you need to ask. Now, if you look at A plus, how is it defined? It is defined as 1 by root 2 m omega by h cross power half x minus I. Then you have 1 upon m h cross omega power half, and then you have over here px. Correct? Yeah, this is how you define it, isn't it? Now, what do I need to do if I want to see whether it's Hermitian or not? I need to take the transposed conjugate, or I need to take the adjoint. When I take the adjoint, I'll have to essentially do 1 by root 2 m omega by h cross power half x minus I 1 upon m h cross omega power half px. Okay, I have to take the dagger of this whole thing, right? Now if I do that, please remember these are just numbers, okay, and they are, moreover, they are real numbers, right? This is the mass, correct? M is the mass, omega is the angular frequency, h cross is the Planck's constant. These are all real numbers, okay? So thereby we don't have to really worry about this constant here and this constant. We have to worry about the I, because it goes to its transposed conjugate. So when you have transposed conjugate, each element is going to be replaced by its complex conjugate. So what is the complex conjugate of I? It is minus I, right? So minus I, so I will go to minus I. So you will get a minus of minus I, so you get a plus I. So let's have a look now. What will you get? You will get 1 upon root 2. Okay, I don't need to put this flower bracket anymore. I will have over here m omega by h cross power half. I'll have x dagger plus I 1 upon m h cross omega power half, and here I will have px dagger. Okay, this is what I'll get. But I know that both x operator and px operator are Hermitian operators. So thereby I know x dagger is nothing but x, px dagger is nothing but px. So what do I get now? I get 1 upon root 2. I will get over here m omega by h cross power half x plus I 1 upon m h cross omega power half px. Now if you look up the definition of A minus, you will realize this is nothing but A minus. Okay, so you have now A minus. So therefore we have the situation that A plus dagger is equal to A minus, and of course A minus dagger is equal to A plus, which means that the transpose conjugate or the adjoint of these operators is not the operator itself. When you try to take the adjoint of A plus, you get A minus. When you try to take the adjoint of A minus, you get A plus. So therefore, A plus and A minus are not Hermitian. See, I want to emphasize this point. Not every operator is Hermitian. It's not that even the most useful operators are Hermitian. All you have to remember is that operators that are linked to dynamical variables, real physical dynamical variables like position, momentum, energy, angular momentum, these are Hermitian. But your all operators which are actually useful for you need not be Hermitian. And these are first examples you're getting of two operators, A plus and A minus, okay, which are actually not Hermitian, but they are going to be very, very useful for us. Now, what is the second thing that we're going to do? So the first thing, we have proved that these are not Hermitian operators. Now the next thing, which is very, very important, I've told you commutation relations are extremely important. Okay. In fact, you will find later on that we define certain things from their commutation relation. Okay. We will say this is such a thing. Why? Because it follows these commutation laws. They are that important. So obviously, since I've been harping on commutation, commutation, commutation all the time, we need to figure out what is the commutation between A plus and A minus. Okay. So in fact, we will do the reverse. We will find out what is the commutation between A minus and A plus. For this, please remember that you will need this, okay, the commutation between xpx. It's a little complicated because we don't know what is, we know that x and px don't commute with each other, okay. So I'm going to now change the page and work this out in the next page. All right. All right. So now if I want the commutation of a minus a plus, okay, obviously I need to do a minus a plus minus a plus a minus, okay. So first I'm going to work out this, a minus a plus. So let us write down what is a minus and then we will write down what is a plus. So a minus, as I have written over here, is 1 by root 2, and then you have m omega by h cross power half x plus I, and then you have 1 upon m h cross omega power half px, correct. And then we will write down what is a plus, which is nothing but 1 by root 2, and then you have m omega by h cross power half x, and then you have minus I 1 upon m h cross omega power half px, okay. So I hope everybody is with me so far. Nothing new complicated that I have actually written. It looks a little ugly, but the reason but what I have done is that I have just written down a minus and a plus in terms of x and px. Now what good news for you is that once we have figured out the commutation between a minus and a plus, we will not really need to come back to x and px again, okay. Yeah, we will do that at the very end, but right now we'll be able to get rid of it for next 1 or 2 classes, okay. So that's a good news. So let's just do this ugly thing. So what we are going to get is that you realize there's a 1 by root 2 here and a 1 by root 2 here. So I'm going to pull it out together and I'm going to write it as half. And then what do we have? We'll have first term here multiplying the first term here. So what will we get? We'll get m omega by h cross and we will get x square. Correct? Yeah, that's our first term. Then our second term will be again this term, and now I'm going to multiply it with this. So of course I'm going to get a minus I, correct? Then I am going to have this m omega by h cross power half multiplied 1 upon h cross omega power half. Now what you will realize is that m omega here and the m omega here will cancel, and you will have 1 upon root h cross 1 upon root h cross. So you will get essentially 1 by h minus I by into 1 upon h cross. That's what you will get. And of course x is first and px is second. So you will get x px, okay. Now then you will multiply this term with this term here, okay. I'm sorry, I included the 1 by root 2. Actually that has already been taken out. So when you multiply again, you have 1 upon m h cross omega power half, and here you have m omega by h cross to the power of half, and when you multiply you will get a plus I into 1 upon h cross, and here you will get a px x, okay. The last term you will get essentially, you will have a I over here, you will have a minus I over here, and I into minus I is essentially what is it? It's plus 1, right? Yeah, I square is minus 1, minus I square is going to give you plus 1. So you will get essentially plus 1 upon m h cross omega, and you will get essentially px square. Okay, so this is what you get. Now, oh, sorry, I made a mistake. You have a No, this is correct. So then you let us just rearrange this. So we will have now over here m omega by h cross x is square. All right, and then we can take out a minus I over here and minus I by h cross over here. And what will we get over here? We'll get an x px, and I'll get a minus pxx, right? Okay, and I'll get a plus 1 upon m h cross omega px square. Now you know what this is, right? This is nothing but the commutator between x and px, and this is equal to I h cross, right? So we are going to put I h cross over there. So we'll get a half, we will get an m omega by h cross x square minus I by h cross into I h cross, and you will get a plus 1 upon m h cross omega px square. All right, so what we get over here now is half, we will get m omega by h cross x square. So here what are you going to get? The central term, h cross and h cross will cancel. You will get a minus I square, and that is nothing but plus 1. All right. So we get essentially a plus 1, and then you get 1 plus 1 upon m h cross omega px square. Okay, so this is for a minus a plus. Now what do? We go back here on top and we try to find out what is a plus a minus. So let us do a plus a minus. I'm not going to do it as elaborately, but I will just write down the basic steps. So you will have again 1 by root 2. What is the form of a plus? It is m omega by h cross power half x minus I 1 upon m h cross omega power half px, right, into again 1 by root 2, and here you will get m omega by h cross to the power of half x, sorry, I was forgetting the x in my, let me just cancel all this, let's write the x, and then you have plus I 1 upon m h cross omega power half px. All right, so this is what you have. So this is going to be nothing but 1 by 2 again. So now we will multiply. What will you get? You will get m omega by h cross x square. Then you will get essentially plus I 1 upon h cross x p x. Then you will get minus I 1 upon h cross p x x, and then you will get lastly plus 1 upon m h cross omega, yeah, px square, right? Now let's see what we get. We get half of, okay, this is m omega by h cross x square, and then we can write it as I by h cross. We have over here x px minus pxx, right, plus 1 upon m h cross omega px square, right? So now again we use the commutator relation, xpx minus pxx is nothing but I h cross. So what do we get? We get half, we get m omega by h cross x square plus I by h cross into I h cross, okay, plus 1 upon m h cross omega px square. So what will this give us? The central term, one second, term, sorry, not town, is equal to half, and then we have m omega by h cross x square. Here we'll have h cross and h cross cancel each other out. We have an I square. I square is nothing but minus 1. So we'll get a minus 1 plus 1 upon mh cross omega px square. Now what is the commutator between a minus a plus? It is nothing but a minus a plus minus a plus a minus. Okay, so let us write it down. This is going to be half m omega by h cross x square plus 1 plus 1 upon m h cross omega px square, right? Minus half, and then we will need to write this term down, which is nothing but m omega by h cross x square minus 1 plus 1 upon m h cross omega px square. I hope it's not looking too horrible. So this is now equal to, as you can see, this term and this term cancel off. This term and this term cancel off. What are you left with? You're left with half plus half, which is equal to 1. Okay? So thereby, the commutator between a minus and a plus is 1. All right? So let me just write it down in the next page. So therefore, commutator of a minus a plus is equal to 1. The very, very important result. Please, please, please remember it. Now out of this comes some interesting relations. We will just write those down. What's the time right now? We have some time. Good. All right. So let's just try and write down the relations which come out of this. So we know that the commutator a minus a plus is equal to 1, which implies that a minus a plus minus a plus a minus is equal to 1, which implies that a minus a plus is equal to 1 plus a plus a minus. Okay, this is a little important relation. We can remember this. Another way to remember this is that how do we write this? We took that to the other side. Yeah, we could take this to the other side and bring this back. So we can write a plus a minus is nothing but, what's happening to me? A minus a plus minus 1. Okay, so this is another important relation. All right, so where are we going to really start using this? I would like you to recall that the Hamiltonian, how did we write it down? The Hamiltonian, we wrote it down as h cross omega by 2. Okay, and then we had a plus a minus a plus. Correct? This was the Hamiltonian. Now what we can do is we can write the Hamiltonian completely in terms of a minus a plus, or we can write it completely in terms of a plus a minus. Okay, so let's say Hamiltonian in terms of a plus a minus alone. Okay, so what will we do? We have h is equal to h cross omega by 2. We will keep this a plus a minus as it is, but then this a minus a plus, we'll replace it with this expression here. So we'll have 1 plus a minus. So this is, it tells us that h cross omega by 2, it's going to be 2a plus a minus plus 1. Or we can do better, we can take in this half, so we will have this this implies that the Hamiltonian is going to be h cross omega, and then we have a plus a minus plus half. Okay, this is again a very important relation. Okay, now we can do further. We can do the Hamiltonian in terms of a minus a plus alone. Okay, so when we want to do it in terms of a minus a plus alone, what do we do over here? We will say h is equal to h cross omega by 2, and then instead of a plus a minus, we use this expression. And what is that? We have a minus a plus minus 1, and then we have, of course, plus a minus a plus. So what will we get over here? H cross omega by 2. Here we have 2a minus a plus minus 1. And then we say this implies that your Hamiltonian is equal to h cross omega into a minus a plus minus half. Okay, again, a very important relation. Okay. All right. Now, so we've done this. So one of these actually has a special name. Okay. We have this a plus a minus is sometimes also called n. All right. It is sometimes called the level operator or the number operator. It doesn't matter. So in terms of n, you can see, okay, let's go here, that your h can be written as h cross omega into n plus half. Okay, so this is another important thing that it will be good to remember. Okay, so I'm going to put this also in a box. Okay, where of course, please remember your n is equal to a plus n is equal to a plus a minus. It's this combined operator which you are talking about. Right. Now we have found the commutation relation between A plus and A minus. Which is our other important operator over here? We had position, we had momentum. Position and momentum we have combined, we have made a khichdi. And then we have put one as A plus, one as A minus. And we have found the commutation relation between A minus and A plus. Using, of course, the commutation relation between X and Px itself. Now what is left? What is left now is essentially to find the commutation relation between A plus, A minus, and of course the Hamiltonian, right? The Hamiltonian is the other very important operator for us. Why is it important? Because it's the energy operator. After all, why are we doing all these things? Because we really want to know what are the energy eigenvalues. Okay. We need to know the energy eigenvalues, and we also need to the energy eigenfunctions are not so important, right? As long as we knows the energy eigenvalues, as long as we know what to measure, what our measurements we are going to come out, we are selfish that way. We are happy. We don't need to sit and solve for the wave functions if we can avoid it. Okay, so we are going to do that. We are going to be a little clever. Instead of first finding the wave function and then doing some khichdi on it and then getting our energy eigenvalues, what we are going to try and do is just get the energy eigenvalues and we are happy. All right. So obviously the Hamiltonian is extremely important for us. And as I said, we have introduced these two new operators, A minus and A plus. Commutation relations are very important for us. So we need to know what is the commutation between the Hamiltonian and these operators. Okay. So let us start off with the commutation relation between the Hamiltonian and A minus. I hope you are able to hear me properly, all of you, because I've been twisting my microphone. You know, I'm paying attention to the class, so I'm not realizing which way my microphone is pointing. So if it's pointing, it's an external mic. If I'm not audible properly, please tell me. Okay? Yes? Sumant, are you awake?
Yes, ma'am.
Thank you. You can hear me, right? Yeah.
Yes, ma'am.
Fine. Good, good, good. So let's try it now. Okay, so we have an operator. We need to find out what is the commutator between H and A minus. So what is this now? So we need to find this out. So what is this? We know that okay, I need to somehow place this size scribe in a more sensible way. Not getting good purchase for some reason. All right. So what will we do over here? Yeah. So this is going to be, so your H A minus commutator is nothing but H A minus minus A minus H, right? We know this. So now let us write down what is the form of our Hamiltonian itself. So which is the form that we are going to take? We can take either form that we feel like. Just one second, let me just see what I have done over here. Okay, so I seem to have picked up the form here. Okay, I will write the Hamiltonian like that. Okay, so what is the Hamiltonian now? It is nothing but H cross omega, and then I have A minus A plus minus half, and then of course I have an A minus sitting here. Okay, so that is this term which I have written, and then I have a minus. Okay, I'll have an A minus, and then the Hamiltonian will be H cross omega A minus A plus minus half. I hope everybody understood this. Now unfortunately I'll have to change page. Okay, yeah, I think poor Gagana is having a bit of trouble today. Yeah, I hope she's back with us. Yeah, so now let us see how we are going to do this. Okay, this particular commutator. So just give me a second. Yeah, I'm going to change the page here. All right. So what do we have now? We have essentially, okay, I have lost track of what we have. Let me have a look at it. So we are essentially trying to work out the commutator between HA minus, and then, okay, I'll just repeat the last step, okay, because I'll never remember it. We have H cross omega, and then we have A minus, A plus, and then we have a minus half, right? Yeah, minus half, then you have an A minus here, minus A minus, and then you have H cross omega, A minus A plus minus half. So let's now expand it. So when we expand it, what will we get? We'll get, and so let's take out the H cross omega anyway, because we don't need it really. Open this out. Then we'll have A minus A plus A minus, right? Then you'll have a minus half A minus, then you'll have a minus A minus A minus A plus, and then you'll have a plus half A minus, right? So when you have this, please remember this term here and this term here will automatically get cancelled. Now what are you left with? You're essentially left with uh, H cross omega, and then you have over here an A minus A plus A minus, and then you have a minus A minus A minus A plus. So what I'm going to do is I'm going to take out this A minus common. Okay, so what will I get? I will get H cross omega A minus, and then I have over here A plus A minus minus A minus A plus. What is this the commutator of, please? A plus A minus minus A minus A plus.
One,
It won't be
one.
1, no? What is 1?
It's constant.
Yes, of course, 1 is a constant. You're
Commutator.
absolutely right. What I'm saying is the commutator A minus A plus. So remember, commutator of A minus A plus is equal to 1. A plus A minus minus A minus A plus is the commutator between A plus A minus. Now can you tell me what is this?
Minus 1.
Absolutely correct. Okay, you remember commutator of AB is nothing but minus commutator of BA. So this is going to be minus 1. All right. So what we will get now over here is that H A minus commutator is equal to H cross omega A minus minus 1. So it is equal to minus H cross omega A minus. Okay. So this is your commutator H A minus. Everybody good? You've got this? I hope. Any problem? Everybody has understood this? How I got this?
Yes, ma'am.
Once
Yes,
you know
ma'am.
the relation of the Hamiltonian in terms of A plus and A minus, once you know the commutation relations between A minus, A plus and A minus, this should be, it should just follow. Okay, so it shouldn't be a problem. What is the next commutator relation that we should work out? We should try and work out what is the commutator relation between H and A plus, of
And A
course.
plus.
Yeah, absolutely. Yeah, so we are going to try and do this now. So again, let's just start off. H A plus commutator is nothing but H A plus minus A plus H. Again, let us see what we can put instead of H. And here I have actually used the other relation. So here I have used the relation A plus A minus plus half. Okay, this is what I have used as the expansion for H in terms of A plus A minus. Instead of putting both A plus A minus and A minus A plus, I've done it only in terms of A plus A minus. Okay, and then of course we have an A plus here minus A plus, and then we have H cross omega, and then we'll have an A plus A minus plus half. So what is this going to be? We'll again take out the H cross omega common. We will have over here A plus A minus A plus half A plus minus A plus A plus A minus, and then we have minus half A plus. Okay, and again this term and this term will cancel, and if you look at it over here, we can take out the A plus from the left hand side. We can take it out of the bracket, so we will get H cross omega A plus, and then what do we get over here? We get A minus A plus minus A plus A minus. So this is going to be H cross omega A plus, and this is the commutator of A minus A plus. Commutator of A minus A plus, I just wrote it down here, is 1, right? So we will get H cross omega A plus. This is the commutator between H and A plus. Okay. Yeah. All right. Now, let's see what is the next relation that we have. Okay, so for the next relation, now let's start concentrating upon the eigenvalues. All right, so let us imagine now that we have okay, let E be an eigenket of the Hamiltonian. Okay, so in other words, it is not just an eigenket, it is an energy eigenket. Okay, it's an energy eigenket. All right, so now we know that if we did H operating on this E, you will get essentially E. So what have I written over here, please? Please note, this can be said to be an eigenvalue equation or an eigenequation for H, correct? Yeah, because this E is just a number, and what is this number? It's a special number, it's the energy, correct?
Eigenvalue.
Yeah, it's the energy. We can also say this is the time independent Schrodinger equation. Okay, so please note, the first time I'm bringing in the time independent Schrodinger equation, but I'm not writing it like a full fledged Schrodinger equation like Meera ma'am has been writing. Okay, we are going to try and do it in a more contracted and a elegant fashion over here. Okay, Meera ma'am has a much harder job, poor thing. Okay, she's going to be wrestling with the differential equation over there. But here we are going to do a little bit of cheating and manage to get away, which is why matrix mechanics is actually a very good way of working out certain things. It makes life a little easier. But remember, it may not work all the time. Sometimes you just have to do the solving of the differential equation, which is essentially what is called as the wave mechanics. All right. So now let me change pages. Okay, let me just check the time first of all. Okay, we just have 3 minutes left. All right. Now, what we are going to do, so I'll just explain to you what we are trying to do, is that we want to know, so we understand what this E is, okay? We understand what this E is. Our next effort is to try and understand what does this, just 1 second, what does this A plus do to the E, okay? We need to figure out the action of the A plus on this eigenket, on this energy eigenket. Okay, what does it do? Why are we sitting with this A plus and A minus? I've told you they are ladder operators. I haven't proved anything to you. So now I better do that. So we need to figure out what is this action of A plus on this energy eigenket. Similarly, we also need to do what is the action of this A minus on the energy eigenket. But how do we figure out this action? Yeah, it will produce some new wave function, right? Do we know what that new wave function is? We don't, right? So the question is, how do we find out? So the only way we can find it out is if we can figure out what we have to do a measurement, okay, or we have to get some value out of that new wave function which makes sense to us. All right, so what we need to do is we need to do this A plus acting on E. All right, and on this we should actually apply the Hamiltonian. Then we should see what we get, because once we have done the Hamiltonian, we are now trying to extract the energy, right? Why do you do a Hamiltonian? Why do you do an operator? Because you want to extract information. So by doing this Hamiltonian on this guy, we should be able to figure out what is the action of this A plus on this E. Similarly, we'll also have to do this. Okay, so in the next class, okay, what we will do is we will, the reason why I'm stopping a little early today, I'm sorry, and in fact actually it's already 5 o'clock, but since you people took 5 minutes to join, I usually go on for 5 more minutes. But today my finger is really, I've done some damage to it, it's swollen, so I think it's really beginning to hurt now. So next class what we will do is we will start off with trying to figure out what is this HA plus E and what is this HA minus E. We'll try to figure these two things. Okay, so this is our agenda for the next class. All right, so I will stop my share here, and if there are any doubts I will clear them, and then we will meet for our class, which is when our regular class, which I think will be on 10th. Okay, I will also send you a message about those 2 extras that I need. Okay, and we will move with that. So any doubts please about in all that we have worked out? See, just get comfortable with the math. Okay, and as you move with me through this linear harmonic oscillator, you will also get comfortable with the physics. Okay, I promise you that. All right, so any doubts with what I did today? Yeah, because it looks very strange, we had this position and momentum operator, we understood everything about it. Where is this A plus and A minus coming from? Next week when I explain the action and you see it in your front of your own eyes, I think you will get more comfortable with it. So any doubts so far, please? Any doubts? I can see that some people have already left the class. There are 58 in the chat box, but there are only 54 participants. Any doubts, please?
No, ma'am.
Okay, good.
No,
Thank you,
ma'am.
Ashita. Yeah, thank you. So now the thing is that please look through what I have done today. If you have any doubts, we will start off in the next class when I give the recap for the end part of the unitary transformations as well as for what we did on the linear harmonic oscillator. Please clarify your doubts, and in the meantime, you can always write to me on WhatsApp and ask me whether you have doubts. If you want some extra reading material, I'll be very happy to provide it. Okay. So fine then. Take care. Have a very nice evening. Take care. Keep yourself safe. Keep your family safe. You know that the cases are really going crazy over here. So take a lot of care, each and every one of you. And we'll see each other on Monday. Okay. All right. So I'm going to stop the recording now.